We're going to do 5 problems here that are uniform acceleration problems for us to practice, so hopefully this will help you out. Our first problem says an object falls freely from rest for 8 seconds. What is the distance traveled during the last 2 seconds? So I think it's always important to kind of write down what your givens are, so you kind of know what we're dealing with. So it falls freely from rest. That's always important. That means your initial velocity is 0. We have a time of 8 seconds. And we're trying to find the distance. So I'll put a distance equals question mark. And so you always come over here and you kind of look at which ones you have. In this equation, you don't have final velocity. You would have a. That's another thing we could write down because this thing's falling. So we know our acceleration. We're assuming it's on the Earth is 9.81 meters per second squared. So you come over here. You have a. You have t. You have vi. You could figure out vf right here. But we don't have a distance in here, and we need an equation that has distance in here because we're trying to figure that out. So if you come down here, these are your 2 distance equations right here. And we have d equals vit. We know vi, we know t, we know a, we know t. So we know everything in this equation to be able to figure out d. Here has final velocity in there again, and we don't have final velocity in our equation. So we're not going to use this one. We're going to use this middle one right here. So if I write that equation down, I'll write d equals vit plus 1/2 at squared. I put little curves on my t so they don't look like plus signs. And it falls freely from rest, so this first term goes away. So that's always nice when the first term is vi is 0, falling from rest. Then these equations a lot of times simplify. So I'm going to have d equals 1/2 at squared. Now the problem with this problem is that it says what is the distance traveled during the last 2 seconds. So we have an object, it falls from like here down to here in 8 seconds. And what we're trying to do is figure out how far it falls, what's the distance that it fell from like here, the 6th second, down to the 8th second. And the problem is that this is going to be a lot longer distance because this thing is accelerating, so it's going faster and faster. So in the last second, from 7 to 8, it's going to fall farther distance than it does from 6 to 7. So to do this, you might need to figure out how fast is it going here. If you had an initial velocity here, and you figured out your final velocity down here, then you could use like another equation, like this third equation here, to get the distance. But we can still use this equation right here. This distance, if we want to figure out the distance, we're going to put 1/2 times gravity, 9.81, times what time do we put in here? Well, if we put in 8, we're going to figure out the distance it takes to go from here all the way to the bottom. If we put in 6, we'll figure out how much time how far it goes from here down to here. And then what we would have to do is subtract the 2. So maybe we can do that both at the same time if we think about it. I could say the distance that it takes to fall to the 8th second, subtract the distance that it takes to fall to the 6th second place, will be this distance down here. So what would that be? That would be 1/2 times a times, I'd put in 8 squared, minus 1/2 a times 6 squared. And that will be my distance that it falls from 6 to 8. So this distance, which I'll call change in distance, which is what I'm trying to figure out, equals 1/2 a. I can factor that out, and I could have 64, 8 squared, 64, minus 36, which is 6 squared. And so I'd have change in d equals 1/2 times a, and a is 9.81, but for some of these problems I just might put in 10 just to round it off. You probably should put 9.81 to be sure, but I'm just going to kind of estimate here. And 64 minus 36 is 28, and then change in d equals, and 28 times 10 is 280, and 1/2 of 280 is approximately 140 meters. So that would be the answer for how far it falls during these last 2 seconds. All right, so that's our first problem. Hopefully that one made sense. All right, let's look at the next problem that we have here. It says if the velocity of a train is reduced uniformly from 54 meters per second to 32 meters per second. Okay, so there's an initial velocity of 54 meters per second, and there's a final velocity of 32 meters per second. While traveling a distance, there's a distance of 473 meters. Now the question says how much further. Oh, okay, so that's another distance. How much further in meters will the train travel before coming to a stop? So there's another final velocity. So we're going to have a kind of a first part problem and a second part problem. The final velocity is 0, assuming the same acceleration. Okay, so what we're asking for here really is what is the acceleration? If I figure out the acceleration here, question mark. If I figure out the acceleration, then I can go on to do this next problem. So I need an equation that has VI, VF, and D in it that will give me my acceleration. There's only 2 equations that have D in it. It's these second 2 right here. And I also need a final velocity in there because I have that, and that one would be this third equation. So this third equation is the one we're going to use here to solve for our acceleration. So I'll write VF squared equals VI squared plus 2AD, and that would be VF squared minus VI squared, all divided by 2D would give me my acceleration rate that I want to figure out first. So acceleration would equal final velocity squared, so that'd be 32 squared minus 54 squared, all over 2 times 473. And if we do that on our calculator, we'll see that we get a negative 2 meters per second squared. So this train is slowing down. We know it's slowing down, so it went from 54 to 32. And these are positive velocity vectors, and our acceleration is negative. And so when the signs, if you remember, when the signs of the velocities and the accelerations are opposite, that means you're slowing down. So we're slowing down at a rate of 2 meters per second for every single second. And so now we can figure out how much further in meters will the train travel before coming to a stop. So we have a VF as 0. I guess there's one more thing I didn't write down. We actually have a VI, right? So at what point are we measuring this? Well, we're saying how much further. So our VF up here, 32 meters per second. Our VF in our problem is now going to be our initial velocity for the second problem. So I want to see how much farther it's going to go as it goes from 32 down to 0 with this acceleration rate. So I need D, and there's 2 equations for D. And I have an initial velocity, and I have a final velocity, and I have an acceleration. So I can use this equation here again, VF squared equals VI squared plus 2AD, to figure out the D this time. So this time, it would be this same thing right here, except for instead of A, I'm going to have a D right here. So it's going to be D equals VF squared minus VI squared all over 2A. Well, what is final velocity squared? It's 0. So I'm going to have a minus VI squared over 2A. And if I have if I get my VI squared, that's going to be negative 32 squared over 2 times my a, negative 2, would be a negative 4. And you're going to have a negative and negative, they're going to cancel out. And that is going to give me 256 meters. 256 meters is how much further this train will travel after it's reached its 32 meters per second. So you see in the first 54 to 32 it traveled 473 meters, and it still traveled 256 more meters before it actually came to a stop. It takes a while for a train to stop sometimes. Okay, so good. Let's look at another one. An object with an initial velocity of 2.3 meters per second. Okay, an initial velocity, VI, equals 2.3 meters per second. Accelerates for 12.3 meters. Distance equals 12.3 meters in 6.8 seconds. So we have time equals 6.8 seconds. What is the acceleration? Okay, A equals question mark. What's the acceleration? We have an initial velocity, we have a distance, and we have a time. So whenever we have a distance, there's only 2 equations that we could probably use for that, these two. We do not have a final velocity, and nor do we want to figure that out. Here we have D, we have T, we have VI, and we need to figure out A. So this is the equation here that we could use. So I'll write D equals VIT plus 1/2 AT squared. Okay, and I could rearrange this. I could take D minus VIT equals 1/2 AT squared, and I could take the 2 times this other side, so I'd have 2 times D minus VIT equals AT squared. And I'm trying to solve for my A, so my A would equal, I'll flip this around now is all I'm doing, 2 times D minus VIT all over T squared. Okay, so it would be 2 times, what was my D? It was 12.3 minus, what's my VI? 2.3 times T is 6.8 all over 6.8 squared. And if I put that in my calculator and get an answer, it should come out, and you can check this, it'd be negative 0.144 meters per second, or meters per second squared. Now this might have surprised you, because the question said an object with initial velocity 2.30 meters per second uniformly accelerates. Well, there is uniform acceleration. That's what we have here, but it didn't say in the problem actually whether it's a positive or a negative acceleration. So what we find here is that our velocity up here is positive, and our acceleration is negative. And since the signs are opposite, that means this thing is actually slowing down. And if you look at this problem up here, you might have realized that might end up being the case, because it only travels 12.3 meters in 6.8 seconds. So that's too short of a distance and too long of a time for this thing to actually be uniformly accelerating. If this velocity is getting faster and faster and faster, in 6.8 seconds, you would actually be beyond 12.3 meters. You couldn't confine your motion within that amount of space. And another way to look at this, in fact, is let's say that maybe this isn't accelerating at all. It's constant velocity. It's always 2.3. Well, then how far would it have gone in 6.8 seconds? Well, that's pretty easy. You just take 2.3 times 6.8, and clearly we get something like over 15 meters. So even if it's at constant velocity, it wouldn't have been able to, in 6.8 seconds, it would have been further along than 12.3. So for it to stay within this distance in this amount of time, it had to actually be slowing down. So that's why we got this negative 144 meters per second squared here. So hopefully that problem makes sense. All right, let's do another one. We're going to do 5 problems altogether. Okay, a girl is skiing down a hill. When she reaches the bottom of the hill, she hits a snowdrift at 15 meters per second and then stops. Okay, so my VI would be 15 meters per second. My VF would be stopped, 0. And the time it took to do that is 0.3 seconds. And the question says, how far distance does she penetrate the snowdrift? So I need a distance. And this is unusual here. I have VF and VI, and I need a distance. So there's 2 distance equations right here. And this one has VF and VI in it, and I could find the D, but I don't have the A. And this one has a D, it has a VI in it, and it has a time in it, but again, I don't have the A. So I can't use either of these equations at the beginning. I'm going to use them eventually, but I need to first of all figure out an acceleration that doesn't have a distance in it. So I'm going to use this first equation here because it does not have distance in it. And I want to solve for my A. So I have VF equals AT plus VI. And that would be, so if I'm trying to find for A, it would be A equals VF minus VI all over T, which would equal 0 minus 15 divided by 0.3. And I get an acceleration rate of negative 50 meters per second squared. She is slowing down 50 meters per second for every second, so that's not good. She's going to probably die. So, but there's my acceleration. Now I can use that acceleration to figure out D. So I have an equation here for D. And I could use either one of these here. So I'll go ahead and use that first one since I already solved for D. D equals VIT, that would be 15 times 0.3 plus 1/2 times negative 50 is my acceleration now, times 0.3 squared. And when you do that in your calculator, you're going to get an answer of 2.25 meters. 2.25 meters that she plows into the snowdrift. Now there's actually kind of another way to look at this problem. Her initial velocity was 15 and her final velocity is 0. And whenever we have a uniform accelerating problem, that means they're increasing their speed at a uniform rate. So we can always figure out an average velocity. There's a couple ways to do that. We can take the total distance they traveled divided by the time. Or we could just average the final and initial velocities. If we just simply average the initial and final velocities, that would be the average velocity that it's going to take them. So 15 plus 0 is 15 divided by 2 would be 7.5 meters per second. So now all I would need to figure out the total distance traveled is to take the average velocity. The average distance would be the average velocity times time. So if I can just figure out an average velocity, I can just take it times the time. Well, they gave us a time as 0.3 seconds. So if I just take 7.5 times 0.3, you will notice that I again get 2.25 meters. That might be an easier way to do the problem. Instead of plugging all these equations in, if you just do an average velocity for any acceleration, uniform acceleration problem, get an average velocity, take it times the time, you'll know your distance. So there's another way to do that problem that you might want to be able to think about. Okay, one more problem. A large rock is dropped from a bridge into the river below. So that means our initial velocity is going to be 0. If the time required for it to drop is 1.70 seconds, so there's time, 1.7 seconds, We also know acceleration, don't we? When we drop something, it's going to be 9.81 meters per second squared. With what velocity will it hit the water? Final velocity is what? So you'll notice we have no d's in this equation, so we can't use this one or this one. This one, we're trying to figure out final velocity. We have a, we have t, and we have vi. So this is going to be a really easy problem. It's already set up for us. Vf equals at plus vi. So Vf would equal a, which is 9.81, times the time, which is 1.7, plus the initial velocity, which is 0. So it really gets easy. All we did is took 9.81 times 1.7. And if 9.8 is 1 is about 10, then my final velocity is going to be about 17 meters per second. So when I drop something from somewhere, its initial velocity is 0. If I'm given the time, then all I do with that time is I just take that time times 10. I'll move the decimal over once, so or 9.81. So 17 meters per second. Technically, it's about 16.7 meters per second if you actually use 9.81, which you will have to on tests and stuff. But for the most part, for just checking, you can multiply it by 10 for the gravity. So I hope those 5 problems really helped you with your uniform acceleration type problems, because you're going to have to do a lot of those in the future.